Chi-squared tests that we learned in the previous section are somewhat limited because they only allow for one explanatory variable, and the explanatory variable has to be categorical. So what if you have a quantitative predictor, or if you want to include more than one predictor in the same model? Logistic regression is going to allow you to do that. So this is a study of 100 randomly selected Italian adults, considering whether a person's annual income, and that's in thousands of euros, can be used to predict whether or not someone has a travel credit card. So it is a categorical response still. Either they have the travel credit card or they don't. So we could think about making this quantitative, right? Having y just be 0 or 1, an indicator. So 1 would be that the person has a travel credit card, and 0 would be that the person doesn't. So when we look at our data, we can see it's just zeros and ones, right? It's just a categorical response here. So one thing that we could think about doing would be using a linear model and interpreting the line, the predicted values, in terms of the probability of having a card, right? So in the places where the line is higher, closer to 1, that means that the person is more likely to have a card. Lower means that they're less likely to have a card. There's actually two problems with that. One is that it's making the linearity assumption, right? So in other words, it assumes that the probability changes at a constant rate. But that may not really make sense, right? It could be that, once you get past a certain income, that most people have travel credit cards and that the probability doesn't really go up much more, right? We may not be able to assume that we have that constant rate of change. The other problem is that your predictions can get out of bounds, right? You can already see here a little bit that it's past 1, and if incomes went up, it would just keep going, right? But if we're interpreting this as a probability, it doesn't make any sense to have predictions that are above 1 or less than 0. So this is another problem with this model, right? That the prediction may be out of bounds, and by that we mean less than 0 or more than 1. So an alternative to a linear model is to use logistic regression. So this is related to the transformations like we did in chapter 5. This is called a logit transformation. And you can see that instead of fitting just a regular response variable as our y, we're going to do the log of the odds, right? So when you look at pi over 1 minus pi, that's success over failures. So that's the odds. And we're going to do the log of the odds. So your response variable is transformed. We're using log odds as the response, but then you have the same linear form for the rest of your equation. Okay? You can also rearrange this to get pi by itself, and you can see the equation for predicting pi. So instead of having a constant rate of change, logistic regression creates these S-shaped curves. So it's a forward-facing S if the slope is greater than 0, and it's a backwards S if the slope is less than 0. So we're predicting the probabilities this way. Okay, so let's start with a basic prediction. Your notes should have the question already typed out. So if we wanted to predict the probability, if we're talking about a predicted probability, we're going to use p hat instead of pi. But I'm just going to plug into this equation here using the values from the output. So I've got e raised to the negative 3.518, that's my intercept, plus 0.105 times income, right? So here I'm going to plug in 30 because we're trying to make a prediction for 30,000 euros as an income, and then 1 plus that whole expression again. So if you plug that in your calculator or in R, you'll get 0.409. So that would be the predicted probability of having a travel credit card for a person with a 30,000 euro income. And we can find this on the graph if we go to $30,000 and go up to the blue line. we can sort of get a rough idea of what the predicted probability of having a card would be. Another question we might want to answer is, for what value of x is our predicted probability 1/2, right? Where does it cross over from being most likely they don't have a card to most likely they do have a card? Okay, so if we want p hat to be equal to 1/2, let's think about what we would have to do in this equation, right? Basically, we want this whole exponential expression to be equal to 1, right? Because that would give us 1 over 1 plus 1, which is 1/2. So to get the predicted probability to be 1/2, we want this expression, and I'm writing it in terms of the sample values now, so that's why I'm using b instead of beta, but we want that expression to be equal to 1. Okay, so remember, anything to the 0 power is equal to 1, so we're going to set the exponent equal to 0. And then we just have to rearrange that expression, and we get x equals negative b0 over b1. So we can plug in our values from the output and get that the predicted probability of having a card is greater than 0.5, right? It crosses over the halfway point, when income is greater than this value. So we're going to do negative, and then our intercept is also negative, so this is going to cancel out, negative 3.518 over 0.105, and that comes out to be 33.4, and that's in thousands, so if we want to, 33.4 is 33,400 euros. One other thing you might notice on this graph is that 0.5 also is at the inflection point of the graph. So this is the point where the slope of the line is steepest. So in comparison to a linear model where you have this constant rate of change, here we have a really fast rate of change from, say, 30 to 35, right? The predicted value, the predicted probability changes a lot. So we have a large change in p hat, or the predicted probability of having a card, as we go from 30 to 35. So that seems to be sort of an important point according to this model. Whereas if we look up here at the top, maybe going from 60 to 65,000 euros, we have a pretty small change there from 60 to 65. So we're not evaluating this model. This is just based on the fact that we're using a logistic regression, but it's possible that this could make more sense in the context. So we've looked at some predicted values. In the next video, we'll talk about how to interpret the coefficients themselves.